Hi, I'm Clinton Kolbeck.
And I'm Mikala Fjerstad. We're from South Dakota State University, and this is our video for the IAM3D competition. Our product for this competition is a specialty fabric with radiation shielding properties. For this project, our material is donated by Turner Innovations. The material is called GMAS. GMAS is made up of 16% tungsten and 84% ABS plastic. We chose this material because it's renewable, eco-friendly, easy to produce, and customizable. We hope to use this fabric as a lightweight alternative to lead aprons.
We talked with Dr. Stish, a cardiologist at the Sanford Health Hospital in Sioux Falls. He gave us a great testimony as to why our product may be life-changing.
In interventional cardiology, the operators that do procedure for long enough usually end up with back problems. In one of the surveys of interventional cardiologists, over 50% of these have admitted to back problems, significant back problems, over age of 45.
So, why is it better to 3D print our product? Well, currently GMAS is only available as a 3D printable filament. Even if you could produce GMAS without the use of a 3D printer, it would still be advantageous to print it. With the use of a 3D printer, we can retain customizability and control the inner structure and thickness of the material to fit more specific needs.
The first test we conducted was a simple tensile test using a universal testing machine available to us on the STSU campus. Along with these tensile tests, we also conducted a bending test using the same testing machine. The results from these tests were put into MATLAB, and a code was written to calculate important data such as the maximum stress and strain, yield stress, and the modulus of elasticity for our material. After the tensile and bending strengths were calculated, we utilized our campus's CT scan machine and took x-rays of our materials. This test didn't provide us with numerical values, but the pictures were analyzed in MATLAB, and we were able to determine the ratio of remaining energy in the material based on the darkness of the material in the image.
After the ratios were calculated on the X-ray images, we reached out to Sanford Health and their head of radiation safety to request their help in quantifying our results. They were excited to hear about our project and provided their time and equipment to us for free. The test was actually very modest. We simply covered the recording surface of the dosimeter with our samples while running a CT scan, and it measured the amount of energy remaining after the radiation passed through the fabric.
The results were interpreted by taking the readings from that control test and then calculating the percentage of that initial radiation that made it through each sample. For the bismuth samples, it took between 10 and 15 layers to provide the same amount of radiation shielding as a lead apron, but the tungsten was able to achieve the same in only 8 layers. These results are very promising, as the weight and thickness at 8 layers is still very much less than that of the lead apron.
Overall, we're really excited about our product, and the future goals for our material are huge. We believe that using this material to produce safety equipment and medical radiography could have some very clear benefits and could potentially revolutionize a market that has been untouched for decades. Thanks for listening.